Assalamu alaikum. So in this video we will prove that this gamma function is equal to actually n minus 1 factorial for any integer n. So in this video we will prove this. So let's start. So first of all we have to apply a UV formula here, but we will apply this UV formula in some different way, in different form. Okay, so let's now see which form we will use to evaluate this integral. So this is the UV. So what is the regular formula? We write u, then integration of v, then differentiate u, integration of v, then we make a whole integration here and we stopped here, then find the value, right? But no, we will not do this in this video. So what we will do, we will differentiate this u. So we will have u prime, and then we will again integrate this v. So integrate, so you have a double integral here. Okay, so now let's see that you have a plus here, then minus here. So plus minus plus, plus minus plus is the sign sequence. Well, so you have to again differentiate this u, so you will get u double prime, and you have to again integrate this v, so you will get 3 integral sign here, plus minus plus. Now you have to write here minus, again integrate u, again differentiate u, and again integrate v. Now plus minus plus minus, now you have to write here plus, again differentiate u, 1 2 3 4. Now again integrate v, 1 2 3 4 5. Okay, so you have to do the same thing again and again, and the question is when to stop. The answer is never. You have to do this up to infinity times. But how can that be possible on hand on our paper to decompose this uv up to infinity? But don't worry, because if you have something like, you see, you have t to the power something, so we will choose this t to the power something is equal to u. We will choose this. So let's give you one example. Let's say u is equal to t to the power c, t to the power 3, and you see we are differentiating it, u, then u prime, then u prime prime, then u triple prime. That means we are differentiating u. So if I differentiate u, we will get 3t square. Again differentiate it, we will get 3 into 2 into t. And if you again differentiate it, you see now you have no t here, right? You have just a constant here. And now if you again differentiate it, you will get a 0, because the differentiation of constant is 0. If you again differentiate it again, you will get 0, and if you again differentiate it, you will get 0. That means after some time, when you will get the constant, and after that you will get a 0, you will get a 0, you will get a 0, and you will get infinite 0 here. So you can stop your evaluation here, because the rest of the terms will be equal to 0. Well, so when you will stop, when you will see that the some derivative of u is equal to is some constant, some derivative of u is some constant, you have to stop here, because the rest of the terms are equal to 0 0 0. Well, so let's apply these formulas here. So I will choose this t to the power n minus 1. This t to the power n minus 1 is u, and e to the power minus t is v. Well, so let's start. So first of all, I will write the first term as it is, and then I will integrate v, and I will get this. If I integrate that thing, then I have to write here minus, and let's differentiate this thing. I will get n minus 1 t to the power n minus 2, and if I integrate this thing, I will get e to the power minus t minus 1, and I have already 1 minus 1 here, so it will become plus 1. Well, so now we have the sequence plus, then minus, then again we have to write here plus. So let me differentiate this thing again. So we will get n minus 2, sorry, n minus 1, n minus 2, t to the power n minus 3, and we have to integrate this thing again, and we will get a term like this. Don't be bored, because you just have to find the pattern. Okay, there is a hidden pattern in all the terms, so you have to just find the pattern. So you have written here plus, so now you have to write here minus. So now let's differentiate this thing, and we will get, if I differentiate that thing, I will get a term like this. And now if I integrate this thing, I will get this. And we have to do the same thing again and again. And as I have told you that if you differentiate t to the power something, t to the power something, t to the power something, at some moment you will get the constant. If at some moment you will get the constant like this. So let's write that constant here. So first write n minus 1, n minus 2, n minus 3. After some time you will get 3, then 2, then 1, and you will get here t to the power 0. That means, you see here you have 3 into 2 into 1, and here you will get 3 into 2 into 1 into t to the power 0, right? Because you have 1 here, and this 0 means, you know, if you minus 1 you will get a 0, right? So we can write here t to the power 0, and then you will write e to the power minus t, and here might be plus 1 or maybe minus 1. Let's examine this, what will be the power here. Okay, so let's start. Let's now find the sequence, and let's see what will be the sign of this. Well, so let's examine the first term. You see this term is negative, right? So let's remove this minus 1, and let's write here minus. And let's now look at the second term. You see this second term is also negative. You have a negative sign at the beginning of the second term. And let's now examine the third term. You see this term is also negative. So let's write this minus 1 at the beginning. So you will get a minus here. And the fourth term, and this fourth term is also negative. That means all the terms are negative. So we can say that this term will also be negative. So let me remove this plus minus 1 here, and let's write the minus at the beginning of this term, and secondly, let's examine that you see this is 1 at this term. At this term, let's see that this is 1, and the next number of 1 is 2, and this is right here. Now in this term, you see you have a 2 here, and the next number of 2 is 3, which is over here. Now this number is 3, and the next number of 3 is 4, which is over here. That means we can write this n in different way. We can write this 1 in different way. We can write 1 like n minus 1, right? We can write this. So now let's see that this number is 1, the next number is over here. That means this number is n minus 1. So the next number is simply is equal to n, because n minus 1, if you add 1, then you will get n, right? So this is n, and the next number of n minus 1 is simply is equal to n. So let me tell this pattern again. You have a 1 here, and the next number is 2. You have a 2 here, and the next number is 3. And similarly, you have a n minus 1 here, and the next number of n minus 1 is n. Okay, And don't forget one thing, you see you have the range of t, so you have to apply the range at all the terms. So let's write 0 to infinity, and as I have told you that there is infinity terms, right? But as you have obtained a constant here, that means the rest of the term is 0 0 0 0. So let's stop here and don't write that infinite 0. Well, so now you see you have two type of terms here. Now listen to me carefully. You see, you at this term you have t to the power something, at the second term you have t to the power something. That means at the all term you have t to the power something, t to the power something, except the last term, because at the last term you don't have any t, because t to the power n minus 1 means 0 and t to the power 0 means 1. So at the last term you don't have any t or t to the power something. That means you have two type of terms. So let's first examine the first type of terms where you have t to the power something. So let's say you have some power t to the power, let's say m, then you have e to the power minus t, and you will apply this limit 0 to infinity over this term, so 0 to infinity. Well, so now we have to, let's write this thing like this, and now let's apply this limit. So first of all I have to put this infinity on t, so limit t to the power infinity, t to the power m, e to the power t, minus, now we have to put 0 here, so limit t to the t tends to 0, t to the power m, e to the power t. So the second term is so easy, you just have to put this 0 here, so you will get 0 to the power m and e to the power 0. That means this term is equal to 0. But you have to focus on the first term, because if you put this t here you will get infinity, if you put this here you will get infinity. So infinity by infinity, that means you have to now apply L'Hopital rule. And what this L'Hopital rule says, we have to differentiate the numerator, so let's differentiate this thing, and we have to differentiate the denominator, so it is simply is equal to e to the power t. Now again examine putting this t to the power t tends to infinity here, you will again get infinity, and if you put this here you will again get infinity. That means you have to again apply the L'Hopital rule. So that means you have to again differentiate this thing, and if you again differentiate this thing you will get m minus 1 t to the power m minus 2, and this differentiation is always same. Again you see that no infinity by infinity, so you have to again differentiate this thing, and again infinity by infinity, so you have to do this up to 3 2 1. When t vanishes you have to differentiate up to this. Well, now let's examine this thing. Let's put this value here, so no t at the numerator, so let's write m factorial. You see this is actually the m factorial, right? And let's put this t tends to infinity here, then we will get e to the power infinity, and we was working to prove that this term is equal to 0. So that means the term which has t to the power something is simply is equal to 0. That means this thing is equal to 0. If you apply the limits here you will get 0, if you apply the limits here you will get 0 0. That means all the term will be equal to 0. But now let's examine this term. Okay, you see we have a constant here, and then we have only e to the power minus t. So let's now apply this range over e to the power minus t. So let's see. So e to the power minus t, let's apply this range over e to the power minus t. So now let's put this value here, then we will get this, and if I put 0 here, we will get this. Though it's not the correct way to just apply these values, because actually t is not equal to 0 or not is equal to infinity. Actually t is tends to 0 or tends to infinity, but to easily teach you that, I have put this value. Well, so no problem. So this is actually equal to 1 by e to the power infinity, and this is simply is equal to e to the power 0. This term will be equal to 0, and e to the power 0 means 1. So the last term is equal to minus 1. Okay, so let's put this value minus 1 over here, and let's see what happens. So first of all, we have a minus here, so let's write this minus here, and then we don't have any space, so let me remove this stuff. Well, let me remove this stuff, we don't need this again. Well, so now let's start. So we have a minus here, then you see that this thing is simply is equal to n minus 1 factorial, and then if you apply those limits over here, you will get a minus 1. So the final answer is n minus 1 factorial. So that means, what was our goal? Our goal was to prove that this is equal to n minus 1 factorial. So that means that gamma n, or 0 to infinity e to the power minus t to the power n minus 1 is simply is equal to n minus 1 factorial when n is some kind of integer. But wait, this gamma function not only applies when n is integer, rather this function can be used on any type of n. Okay, n can be 0.5 or n can be 3 by 2, 4 by 3, anything, right? So at the next video we will see that what is gamma half. Well, so see you in the next video.